Hello my friends, this is a short video on magnetic torque on magnetic dipoles. Learning objectives are conceptually understanding magnetic torque and determine the rotation direction of magnetic dipole in a magnetic field. We won't be really talking about calculations and mathematical applications of it too much. So the idea here is that if we put a magnetic dipole, which would be a current loop actually, the current loops we were talking about are actually magnetic dipole. And what is a magnetic dipole is that when we have a bar magnet, that's not south, north, that's south. It has north and south, two poles. That's a dipole. And this is how its magnetic field lines look like, away from north always. And actually rolls back, comes in towards south. And this is a magnetic dipole. And we already talked about how current loops also has a magnetic field in their center, and we may make them, they do resemble actually to bar magnets. We can draw a bar magnet right in the center of a current loop, and the direction of magnetic field will be the north, the other side will be the south pole, and the magnetic field lines will also look identical to a bar magnet. So this is what is a magnetic dipole. It has two poles, north and south, and this is how its magnetic field lines look like. They also have what we call magnetic moment, and we represent magnetic moment with mu, and it can be easily calculated using current times the area of the loop, and this loop's area here would be this area. So anything that has a magnetic moment, which is generated by current as well, will be rotating inside a background magnetic field. And how it will rotate is that, as it's nicely shown in this figure here, it will rotate, so it will align along the magnetic field line, the background magnetic field line, the blue line here. So what we'll be looking at, which direction it will be rotating, and will it rotate until it's perfectly aligned parallel to magnetic field, or anti-aligned, it will rotate. That's the idea here. The main reason for our compasses to rotate along the direction of magnetic field of the earth actually was because they want to align along the magnetic field lines. And our book resembles this to a pendulum aligning along the gravity. So it's a very similar idea here. This question here is a type of question we might see in the exams or problem sets. If released from rest, the current will rotate or not, and if it will rotate, how it will rotate. This current loop is actually coming out of the page here. I'm going to try to draw it. Goes around and goes into the page there. So if I use my right hand rule to curl my fingers along the current here and open my thumb, it's not very easy to draw, but my thumb will be down here. Do this with me with your right hand. You will see, curl your fingers along the current, which is here, and this direction comes out of the page and goes into the page on this side. You will see that your thumb is, open your thumb, it will be directed downward. That's going to be the magnetic field direction of the loop we learned, and the magnetic moment direction is also the same. So I'm going to show the magnetic moment here. Again, it's current times the area of the loop. So what will happen here? Will it rotate or not? If it will rotate, which direction? It will rotate to align itself with the magnetic fields. It will rotate in this direction until mu is parallel to B. And that's the direction, counterclockwise. So it will rotate counterclockwise. And the reason for rotation is there is a net torque. We could talk about how forces are applied up and down here. This is actually magnetic force, but we won't be going into that much detail. It's very simple matter to understand which direction it rotates after we find the direction of mu. It will rotate in the shortest direction it will take to align with the magnetic field. This question is more subtle here. Two nearby current loops are oriented as shown in the figure. Loop 1 is fixed, so this guy is fixed here, can't move. And loop 2 is free to rotate, and will it rotate? If I use my right hand rule I can find the direction of magnetic field or the magnetic moment of this guy to be to the right, so magnetic moment I'm going to show in the center, and it's to the right. And I'm going to look at the magnetic field direction. I'm going to call the magnetic field of loop 1 B1 at the point of B2. What is the direction of B1 at the point of loop 2? For that, I'm going to use my right hand rule again to find the direction of magnetic field of this guy. If I roll my fingers along the current and open my thumb again, my right hand rule tells me that the magnetic field is down here. So B1 is down. Then I need to go into details here to draw all the magnetic field lines outside as well, so I will see how they look over here. If the magnetic field is down, the direction of magnetic field will be the north, the other side will be the south, and the magnetic field lines will go from north to south. So I draw them away from north, goes around and comes back to south. Same on the other side. So that's the direction of magnetic field lines. As we talked about the magnetic field lines, we learned that they keep going, right? We have many magnetic field lines. If we have them close to each other, they are stronger. If we have them farther away, they are weaker, and so on. So these magnetic field lines will keep going. They are actually everywhere. Field, right? That's how field behaves. They will keep going, keep decreasing in strength, but they will be everywhere to infinity. So if I draw a magnetic field line at the point of this guy, I didn't do a great job there, but it gave us the idea that magnetic field B1 should be going upward here. Then what happens? Mu, the magnetic moment of this guy, I'll call it mu1 actually, is to the right, not aligned with B1, so it will rotate to align with B1. Which direction? Counterclockwise again. That's the general idea here. This one is explaining what I've just explained to you. It will rotate and align and so on. This very idea used in magnetic resonance imaging techniques. We send a strong magnetic field into the body of a person, and all the protons aligns along the magnetic field lines. And then we turn off the magnetic field for a while, and the protons realign with their original position. They emit a current. We read that current and we map it to understand how the tissues in the body is oriented and so on. This picture here is showing a picture taken with MRI. What this gives us is if the tissues are normal, if there's any abnormal situation, cancerous cells or so on. Electric motors works in this idea. Magnetic fields rotate in a current carrying loop, because current carrying loop will have a mu here. This picture here is a symbolization of it. If I have a mu, I apply magnetic field to the right, it will rotate to align with that magnetic field, and we can use this idea to generate motors. This figure is showing that, and this is a toy that does the same. Under this box here we have a battery. when we put this wire, conducting wire, and here the current starts passing through. Let's say current is passing through in this fashion. I'm going to just write here. And this loop will have a current. It will be a current loop, right? If it is a current loop, it will have a mu. Using my right hand rule again here, applied with me, I will see that my thumb will be upish here, a little tilted right, so I'll have a mu in this direction. Then what we do is we put a magnet here. This round black thing is actually a magnet. And let's assume that the magnetic field lines are down. It could also be up, it doesn't matter. It's rotate mu. It will rotate towards the direction of magnetic field line to align with them. It will be rotating in the other direction if we have magnetic field up. So in this case, it will rotate clockwise. We use this idea to build electric motors. Notice as it aligns with magnetic field, it will stop. So to get it going, what we do is we turn off the current, gravity pulls it down, and then mu turns into the other direction. So then we have an angle between magnetic field and the magnetic moment. It starts rotating again, comes to the same point. Same thing happens. We turn off the current and keep it going in this fashion. It turns out, as we learn from science and investigation, that that's how the magnetic materials work. We call magnetic materials ferromagnets, and they have electrons, protons in them. Mostly electrons are outside in the atom, so they are more effective. And they all have their own tiny magnetic moments because they are spinning. So they have tiny current loop. That tiny current loop is causing a mu. In a non-magnetic material, all these mu's, the magnetic moments, are in different directions oriented. When we add them as vectors, we get over a zero. But for a magnetic materials, they don't go to zero. So they have an overall addition of magnetic moments adding up to a magnetic field and causing the magnetization and magnetic force around them. Here is how a perfectly aligned system magnet would look. In real life, they're not really perfectly aligned, but most of them align, so we have an overall magnetic field in this direction. If a ferromagnet is not totally magnetized, we have domains of alignments. For a non-magnetic or materials that are not affected from magnets are called diamagnetic materials, and there are rare alignments in them for the spinning electrons' magnetic moments. But for ferromagnets like iron, there are domains of alignments. And these domains of alignments can easily be aligned all together if we apply a magnetic field, which is why they align and they're attracted by the magnetic fields. And this picture is nicely showing that if we wait a bit later, all these domains, most of these domains will align along the magnetic field, and we will have an iron to be attracted to the magnets. Iron actually has a specific property that it can stay as aligned for a long time, and it can itself become a magnet. And if that happens, it becomes a magnet. And if we apply a strong magnetic field, especially, that happens. And after a while, they realign, but it takes a long time to realign. We can help them realign faster if we heat the iron or hit it with the hammer or so on. CDs, recording of sounds and pictures, uses magnets to work, and computer reads them using the tiny magnets inside. So the long magnets are rated as 0, short ones are rated as 1, and everything is stored in this fashion. Electromagnets are formed by putting an iron core inside a solenoid. This picture is nicely showing that this is a solenoid, and we already learned that if we send a current through a solenoid, in this picture here, it would go here in this fashion in the back and comes out here, and this solenoid would have a magnetic field upward. If we put an iron bar inside it, and inside the iron, domains will mostly align with that magnetic field, and what happens is that iron becomes strongly magnetized. It adds up to the background magnetic field of the solenoid. Let me call this B iron. So they kind of become one big strong magnet together, and the total magnetic field would be these two added in the center. We can simply build this using a iron nail, and putting wires around it. It's pretty nice and easy to see. With a battery, we can see that after we send the current, this guy becomes a magnet and it can pick up stuff. That's all I'm going to tell you about this. See you on the next lecture.